Good day, everyone. Welcome to the first lecture in the series General Inorganic Chemistry, and today we'll be talking about electronic structure. So, in order to talk about electronic structure, we have to start off with the history of the atom, and we also need to know that all matter is composed of atoms and that if we understand the structure of atoms, then that will give us insight into the properties of matter. And properties of solid materials depend on the geometrical atomic arrangements, and that is why we want to get into it and the interactions between constituent atoms. So, of course, atoms form molecules. So, if we understand atoms, then we can therefore understand molecules. So, firstly, going into the history of the atom, we meet Democritus, and he was the first who started off by pounding up materials with his mortar and pestle until he reduced these materials to very small, the smallest of particles, and he called that atoma, and that is Greek for indivisible. So literally the smallest particle pieces until it cannot be divided any further, and hence indivisible. And the second person that we want to talk about here is John Dalton in 1808. He suggested that all matter was made up of tiny spheres that were able to bounce around with perfect elasticity, and call them atoms. So, going deeper into the history of atoms, we therefore meet upon J.J. Thomson, who he found that atoms could sometimes eject a far smaller negative particle, which he called an electron. So, we're just speaking briefly about the conclusions that they came upon based on their experiments. So as you have seen, we haven't looked at the experiments. We're basically just looking at the conclusions of these experiments. And so he would have done a series of them, and based on that, he found that the atoms, they are not the smallest particle. There is an even smaller particle, which he says is negatively charged, and he called that particle an electron. So further in the history, we then meet Ernest Rutherford, who in 1910 he proposed a more detailed model with a central nucleus. So clearly here we're going deeper and deeper from somebody just dividing pieces of material with a mortar and pestle into scientists going further and further into the structure of the atom, right? And so Rutherford, he proposed a more detailed model of the central nucleus. And for him, this is positive, or based on his experiments, he concluded that this central nucleus is positively charged, and it was the central nucleus, as we said. So with this holding the electrons in place by electrical attraction, right? So J.J. Thomson said that we have these negatively charged electrons, and Rutherford said, okay, well, we have a positive central nucleus that are holding the electrons in place. And that brings us now to Niels Bohr, who in 1913 he refined Rutherford's idea. So I hope you're seeing the trend here that each scientist basically built up on the works and experiments of the previous scientists for further clarity for us as human beings. And so Bohr was no different. He said that, hey, these electrons were in orbits. They're not just static, they're in orbits, rather like planets orbiting the sun, with each orbit only able to contain a set number of electrons. So that's what Niels Bohr said. And the model looked something like this, right? Or looked exactly like this, the Bohr model, right? So he says at the center, we have protons at the nucleus, right here in the center. And we have electrons that are in orbits. They're in set orbits surrounding that positive nucleus. And clearly it's one electron, so this would represent the hydrogen atom. And so Rutherford's model predicted a rainbow of colors rather than discrete lines obtained from an atomic line spectra. And so to explain the line spectra, Bohr proposed that electrons of specific energy moved in circular orbits around the nucleus and could not exist between these orbits, right? And I know you might be wondering, what is this line spectra that we're talking about? Don't worry about it. We're going to speak about it a little bit more in detail. But as we said, because we haven't been looking at the experiments themselves, we've been looking at the conclusions that were made from these experiments. And so he conducted an experiment and he saw these atomic spectral lines. And based on that, his conclusion was that the electrons were at specific energy levels orbiting that positive nucleus. And just to introduce us to two terms here, quantized and continuous. So we liken quantized to stair steps. So stair steps are quantized. They only have certain places where a person may stand. So, I mean, this is self-explanatory. If you're going down a stairs, you can only go from, yes, you can jump, but there are only certain set spaces that you can step on, as opposed to a wheelchair ramp, which is considered to be continuous. It has an infinite number of possible positions. So if you're going up, you can stop at any possible position along the ramp, right? So this is important because that is basically what Bohr was trying to say, that it's more like a step arrangement where these electrons are in set energy levels, and that was the conclusion based on the atomic line spectra. All right, so here we're getting a little deeper into the atomic structure here, and we're being introduced to some key terms, right? So here we have a quantum number which is equal to n, and here we're saying that there's several n. So we have n equal 1, n equal 2, n equal 3, and n equal 4. And that directly correlates to electronic orbits. So K is the first one, L is the second one, M is the third one, and O is the fourth one. And these are called electronic orbits. So this is what Bohr was saying, that the electrons are in set electronic orbits surrounding the positive nucleus, right? And these electrons, he further found that they are shaped, the probability exists that the electrons are not just in a line, but let's hold that for a minute. Let's just stick to what Bohr said. Later on, we'll go into these particular orbitals, which are directly related to these electronic orbits, or where the electrons are found. So these are our atomic orbitals and how they are shaped, and they're directly linked to our electronic orbits, or where the electrons are found. So Bohr's model of the atom in 1913, he said that one, electrons can have only specific or quantized energy levels, as we saw, and two, light is emitted as electron moves from one energy level to a lower energy level. So energy is absorbed and it goes from a lower to a higher energy level, that is the electrons. And if they lose energy, that is, they go from a higher to a lower energy level, they can emit or will emit energy to move from one energy level to the next in the form of a photon. And for the hydrogen atom, that energy is governed by the Rydberg equation, which is equal to minus RH, which is the Rydberg constant, and the number change is basically depending on what we're calculating, or the units of what we're calculating, right? So here we have the Rydberg constant at 2.18 times 10 to the minus 18 joules. And that is, in brackets, we have 1 over n squared, and n represents the principal quantum number, and it's 1, 2, 3, etc. So it's directly related to these quantum numbers here. So going from either 2 to 1 or 3 to 1 or 4 to 3, the energy is emitted, and that is governed or captured in this equation here for hydrogen. All right, so that we have been talking about energy being absorbed or emitted. So let's use the proper terms. So when the electron absorbs energy, it is therefore excited. So that means it has undergone excitation, right? Once the electron loses energy, it is therefore relaxed and therefore has undergone relaxation, right? So the energy loss in the form of losing a photon, right, we call relaxation, and that is accompanied by light emission. And so energy is absorbed for excitation and light is emitted for relaxation. And of course, we see our principal quantum number here, or energy levels, in which the electrons are moving essentially from one level to the next, and it's either absorbing energy or releasing energy. The important point here is that excitation is basically the same as energy absorption, and relaxation is a release of energy, and it is usually accompanied by light emission. All right, so this is just a very nice diagram and just expounding on excitation and relaxation. So if you recall the different energy levels, we have K, L, M, N, and we're seeing here release of energy. And as we said, that is usually accompanied by light emission. And then we have energy being absorbed. Seen here, the electrons are going from the different energy levels. So this is basically a cross section of an atom, and we're seeing a different angle here, but essentially the same information, where we have the positive nucleus and then we have the different energy levels surrounding our positive nucleus. All right, so we did talk about the line emission spectrum from the Bohr experiment and how he came up with the discrete energy levels. Well, this is kind of an example of what was done in that experiment. And so just to simplify, what really happens here is that, clearly the hydrogen atoms would have to be excited, right? And then their relaxation, as we mentioned before, is accompanied by the loss of light, right? The loss of energy, the loss of photon, right? And our natural eyes would not be able to see this separation, and so it has to be we have to use a prism in order to see or observe the separation of the different energy levels, or the line spectrum, right? So this is a line spectrum that is observed and it corresponds to a different wavelength, right? Or a different energy. And so we have our red, our green, our blue, and our violet. And this is what was observed. So the hydrogen would have been excited due to high voltage, and then once it is now returning back to that energy level, as in relaxation, it is accompanied by the loss of light. And in order to observe that, there we use a prism in order to separate the light into its components, and so we can observe the line spectrum seen here. And this is just an example of, well, this is the same line spectrum that would have been observed. The different lines correspond to different wavelengths. And just to give an overall picture of where the lines would occur in comparison to the overall electromagnetic spectrum, right? So here, if we're seeing these colors, it means that this is visible light, right? So the visible here occurs in the spectrum, and then we have our X-rays or gamma rays or ultraviolet portion of the spectrum. We have the IR, and we have the radio waves, from which our TV and our radio, they basically, that is how we are able to have these facilities, right? And so that is directly related to the energy, right? And so these gamma rays and X-rays are the high energy portion of the electromagnetic spectrum, and the radio waves are lower energy regions of the electromagnetic spectrum. So the line emission spectrum of hydrogen atoms, that is, once we can observe it, that means that occurs in the visible region of the electromagnetic spectrum, as we see here. And this is basically saying the same thing that we have been saying, that the transitions, and going a little bit deeper into it now, we're seeing that the red transition is from 3 to 2 energy level, and the blue-green line that we saw, that is the transition from 4, n equal 4 to n equal 2, and the violet is as a result of the transition from n equal 5 to n equal 2, right? So clearly what we're seeing, what we're observing, is relaxation, right? And they correlate to a particular region of the electromagnetic spectrum, and the fact that we can observe it means that these are the transitions that we're seeing, right? And so if we're going to energy level 2, so what we're literally seeing, notice here that all of the transition goes to energy level 2, right? And we can observe it, which means that it's in the visible portion of the electromagnetic spectrum, right? And some new words here, so that is the Balmer series, right? And so whenever you have transitions occurring like this to energy level 2, they occur in the visible region, and they are called the Balmer series, right? And then you have others. You have the Paschen and you have the Lyman. So the Paschen goes to energy level 3, and that occurs in the IR region. And the Lyman goes to energy level 1, and that occurs in the UV region, right? So this is a picture saying the same thing. So as we said, the different colors that we saw correlates to a particular transition to energy level 2, definitely, and that is our Balmer series. But we have other transitions that we cannot see with our eyes because they occur in different regions of the electromagnetic spectrum that we are not able to see. So it was the Swedish spectroscopist Johannes Rydberg noted in 1890 that wave numbers of all the lines in the hydrogen spectra are given by this expression. So we have seen this expression before. As I said, the unit of the Rydberg constant is dependent on what we're calculating over here. So here we're seeing wave numbers, right? So when we have the almost looking V with the line above it, that is wave numbers. And so for this equation, N1, N1, so when N1 is equal to 1, then that is the Lyman series, as we said, that's here. When it's equal to 2, that is the Balmer series. When it's equal to 3, that is the Paschen series, etc. And that in each case, N2 is equal to N1 plus 1, etc. So we're either going from, what is for sure, guys, for the Balmer series, we're always going to 2. Where we're coming from will vary, and that is why N2 will vary. So N2 is where we're coming from. So we're either coming from energy level 3, 4, 5, 6, 7, etc. But for once it's a Balmer series, we're going to energy level 2, seen here. And the constant for the Rydberg constant, as we said, for hydrogen atom is found empirical to have the value 109,677 reciprocal centimeters, right? As I said, you will see various values for the Rydberg constant depending on what we're calculating over here and what the unit is of what we're calculating over here. So here we're calculating wave numbers, and so our Rydberg constant is different from what we had seen earlier when we were calculating energy, right? All right, so we must know what we are calculating. So another diagram here of the electromagnetic spectrum, and this is basically just to say that, you know, we have different units of measurement here. So we have wavelength in meters, we have frequency, which is waves per second, and we have energy of 1 photon, electron volts, right? So these are all units that you will see in our calculation. So you'll see meters, you'll see waves per frequency, etc., right? And as we said, the Rydberg constant will vary depending on what we're calculating. All right, so just to give a little more insight into the electromagnetic spectrum, as we said, for the emission spectra for hydrogen, we saw lines, and that would occur right here in the visible region of the spectrum. But there are other regions that we're not able to see with our eyes, right? And our X-ray, gamma ray region, or IR region, our microwaves and our radio waves, we are not able to see, right? So these are some important relationships here. Here we're seeing that frequency is equal to the Rydberg constant multiplied by 1 divided by n squared minus n prime n squared. So our frequency is actually in hertz here, or second to the minus 1, whichever. All right, they're the same thing. So R, or Rydberg constant for hydrogen, in hertz, that's a different number. So that's 3.289 times 10 to the 15 hertz, right? So we have to be clear on what we're calculating, whether it's energy, whether it's wave numbers, or frequency. And so because of that, we have to be able to interconvert, right? So here, if we calculated the wave numbers, that is directly related to the wavelength by this equation here. And so our wave number is equal to 1 divided by the wavelength. And so if the wavelength is in centimeters, and this is a signal, lambda is the symbol for wavelength, and if it's in cm, then the wave number, centimeters, sorry, then the wave number is the reciprocal centimeters, and it usually has a V bar, right? So the symbol for wave numbers is V bar, and the symbol for wavelength is lambda. All right. And so as we said, just to write it differently, so this portion here is the same as what we have here. So our reciprocal centimeters, or wave number, is equal to 1 over the wavelength in cm. So that is also equal to the frequency divided by c, right? So c is the speed of light, and that is 2.998 times 10 to the 10 centimeter second to the minus 1, right? Centimeters, or we could say per second, right? And so here we can see that the per second will cancel, and so we end up with our wave number seen here, right? So we need to be able to, just play around with these equations. So if you got frequency, you should be able to calculate wavelength based on these relationships seen here. So we have already seen this equation for the wave numbers, which is equal to 1 over the wavelength, which is also equal to the Rydberg constant times 1 over n squared minus 1 over n prime squared. And of course, we know that V bar is equal to wave number, and the Rydberg constant. Once we're calculating wave numbers, guys, notice that the number for the Rydberg constant changes, right? So we have to be aware of what we're calculating, whether it's with energy, whether it's frequency, whether it's wave number, and then the Rydberg constant will, the value for the Rydberg constant will change accordingly. All right, so let's look at this question here. The Rydberg equation, as we saw, right? So determine the frequency of the 7 to 3 transition in the Paschen series in the emission spectrum of atomic hydrogen, right? And so the notation 7 to 3 refers to the n prime is 7 and n is 3, right? So notice what we said about the Paschen series, it always goes to energy level 3, or quantum number level 3. So we use the Rydberg equation in this form, right? So we're calculating frequency. So let's use the equation from here that actually has the symbol for frequency. And we literally, and so just to go back to that slide. So this is the value that we would use if we're calculating the frequency. And so if we just plug in our values here, so we have our Rydberg constant value here. We have 3 is the level quantum number that we're going to. 7 is the number that we're coming from. And once we do this mathematical calculation, we will get the value for the frequency in hertz, right? And just go back to our electromagnetic spectrum here, right? So here we expect, if it's hydrogen, that it would be in this region here, right? So it's either in the IR or the UV region based on what we saw, right? Or just to go back here. So if it's in the Paschen, we actually expect it to be in the IR region, right? All right, just to go further in terms of electronic structure, as we said before, various scientists have basically discovered, or based on their experiments, they have basically come up with the structure of the atom. And so they would have said that in the middle we have our positive nucleus here, with our positively charged protons here, and our neutral particles, which are our neutrons. So in the middle of the atom we have our protons and our neutrons in the nucleus, and then surrounding it we have our negatively charged particles in orbitals surrounding nucleus. So this is basically what you would have been introduced to as the structure of the atom. So every different atom has a characteristic number of protons in the nucleus. So as you would have known, the atomic number, and we will call that Z, is equal to the number of protons, right? So once we gain an atomic number, we all an electron, we gain a proton as well. So for an electrically neutral atom, the atomic number is equal to the number of electrons. So I was a bit ahead of myself there. So the atomic number is equal to the number of protons, and the atomic number is also equal to the number of electrons. So atoms with the same atomic number have the same chemical properties and belong to the same element, which I'm sure you know already. So for the atomic number Z, we're saying it ranges from 1 for hydrogen to 92 for uranium, and this is the highest for the naturally occurring elements. So just to do a little more maths here, the atomic mass of a specific atom, right, would be the sum of the number of protons and neutrons within the nucleus. So the mass number is equal to A, we're calling that A, and that would be equal to Z, which was our atomic number, which we know that would be equal to the number of protons, right, plus the number of neutrons within the nucleus. And so the number of protons is the same for all atoms of a given element, and the number of neutrons may be variable, and that is how we have isotopes. All right, so the reason why the electron does not weigh in as much is because it's small in comparison to the proton and the neutron, right? And so the proton is 1,837 times heavier than the electron, and the neutron is 1,842 times heavier than an electron. So the electron is much lighter with respect to the protons and the neutrons, which is why here the atomic mass is equal to the number of protons plus the number of neutrons. And just to have an idea of the numbers, electrons 9.11 times 10 to the minus 28 grams, as compared to the neutrons and protons, 1.67 times 10 to the minus 24 grams. So very, very small numbers. But the important point here is that the protons and neutrons are basically roughly the same in terms of mass, but they're much more heavier than the electrons. And also to note the charges here. So the electron, as you would have known, would have been -1, the charge, and proton, we know that that's positive, +1, and neutron, we know that that is neutral. All right, so if you look at an periodic table, you will see it set up like this. So for example, we have helium here, and we have our atomic mass number, which is equal to our protons plus a number of neutrons, as we just said. So our mass number here and our atomic number here, and that of course is equal to the number of protons. So we have another question. How many protons, neutrons, and electrons are in iron, right? So we see the numbers 56 and 28. So you should be able to look at this and tell me how many protons, how many neutrons, or how many electrons are in iron. So if you worked it out, you'd have gotten 28 protons and 30 neutrons for iron. All right, so just to go back into, we're going to delve a little bit deeper into our electronic structure here and into the Bohr atomic model. So as we've said, the electrons are assumed to revolve around the atomic nucleus, and we did say in discrete orbitals, and the position of any particular electron is more or less well defined in terms of its orbital, and the electrons are permitted to have only specific values of energy. So we said all of this already, right? However, unfortunately, and according to quantum mechanics, extremely small particles such as electrons, they do not follow the laws of classical or Newtonian physics. And so the new physics that mathematically treats small particles is called quantum mechanics. So we're going away from our classical physics and we're going towards quantum mechanics, which deals with extremely small particles such as electrons. And we did see the term quantized before, but it was Max Planck who developed the idea of discrete energy levels for electromagnetic radiation. That is, that energy is quantized. So you remember the step analogy that we said earlier. So the equation below gives the relationship between energy and frequency and the proportionality constant h, which is called the Planck's constant. And this is the value of Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. That is our proportionality constant that helps us to convert between energy and frequency, right? So I just have an example here just to show the units, right? So energy is usually in joules, right? So the Planck's constant is joule second. Frequency is normally hertz. So as we have seen, our second to the minus 1, which is more appropriate here because we want to multiply and only get joules. So it was Max Planck who developed the idea of discrete energy levels for electromagnetic radiation, and therefore from then on we recognize that energy is quantized. And so this leads us now to the duality of these particles, right? So wave mechanical model of an electron is no longer treated as a particle moving in a discrete orbital. So remember what Bohr said, that the electrons are in a line moving surrounding the orbit, right? So based on the wave mechanical model, an electron is no longer treated as a particle moving in a discrete orbital. And so the electron is considered to exhibit both wave-like and particle-like characteristics. And so the position of an electron is described by a probability distribution or electron cloud, right? So basically, if we have an electron that is surrounding the nucleus, right? And let's look at this diagram for a second, where here on the x-axis it has distance from nucleus, right? So basically what we're seeing here is that as you move away from the nucleus, the probability of finding an electron increases, right? So we have the distance from nucleus here on the x-axis, and we have the probability on the y-axis, right? So as we move away from the nucleus, we're seeing here that the probability increases, right? And then it goes down as we move further away from the nucleus. So here we are going to see that the position of the electron is going to be described as a probability distribution or an electron cloud, in which we're saying that the electron quite possibly, or the probability that the electron is here is high, but it doesn't mean that it couldn't be here or here, right? So wave-particle duality. So it was in 1924 that Louis de Broglie argued that if radiation could exhibit the properties of both particles and waves, something that defeats the laws of classical mechanics, then so too could electrons, and indeed so too could every moving particle. And so this phenomenon is known as wave-particle duality. So the Broglie relationship shows that a particle, and this includes an electron, with a momentum, and you guys would know momentum to be mv, where m is equal to the mass and v velocity of the particle, has an associated wave of wavelength, and we know the sign for, or the symbol for wavelength being lambda here. Thus, the equation combines the concepts of classical momentum with the idea of wave-like properties. So this is the de Broglie relationship that is relating the momentum to wavelength, and of course we have our Planck's constant here, right? So this is further strengthening the wave-particle duality of an electron. So the wave behavior is described by the wave function, and that is a symbol for the wave function, incorporating the wave and particle features of electron. And it was Schrödinger, and well, for our purposes, we're not really going to go into the Schrödinger equation. We just want to get the information, what information was received from this relationship. And it is that the probability of finding an electron in a certain area of space is proportional to psi squared, which is the electron density. So we're not really too worried about the Schrödinger equation. What we're saying here is that this, say for example, this is an atom, right? So if we have a positive center and we have the electrons here. So in the Bohr model, we did see the lines, right? With quantum mechanics, we're saying here that it's a probability that the electron is here, and the probability will decrease the further away we move from the nucleus, right? And that is what quantum mechanics is saying. It's about a probability function. Let me go back to that one. It's about a probability distribution or electron cloud. The probability that electron is in a particular space versus discrete energy levels. And so another scientist that we need to mention is Heisenberg. And because he basically defined the Heisenberg uncertainty principle, which says that we cannot precisely measure the momentum and the position of an electron at the same time. So as the momentum of the electron is more and more certain, the position of the electrons become less and less certain, and vice versa. So here, this is the Heisenberg uncertainty principle, or this equation captures the Heisenberg uncertainty principle, where over this side we have a constant because we have Planck's constant and we have pi, right? So this number is a set number. So the only variables are on the left hand side of the equation, and the delta, which is the capital D for the Greek letter, it represents the uncertainty, right? So whether it's the uncertainty in the position or the uncertainty in the momentum, so this is the momentum as we have earlier defined as being equal to mv. So based on Heisenberg, he said that we cannot accurately measure the momentum and the position of an electron at the same time. So because this is a set number, if we are very certain, which means that the uncertainty is low, then that means the uncertainty in the momentum is going to be high, right? I hope you get that. All right, so continuing to look at the various atomic orbitals, the Schrödinger equation specifies possible energy states an electron can occupy. And so the energy states and wave functions are characterized by a set of quantum numbers. So instead of orbits in the Bohr model, quantum numbers and wave functions describe the atomic orbitals. And what we see here is the probability function of, this is a p orbital. So every electron in an atom is characterized by 4 quantum numbers. So we must know this. There are 3 quantum numbers necessary to describe an atomic orbital. So firstly, we have been seeing the principal quantum number, which we call n, and it designates the size of the orbital. The L is the angular momentum quantum number, and it describes the shape. ML is a magnetic quantum number, and it defines the orientation. So we're not seeing the third one, but each electron, sorry, we're not seeing the fourth one, but each electron is characterized by 4 quantum numbers, and these 3 are necessary to describe an atomic orbital. All right, so let's look at the first one. So the first one, as we said, is the principal quantum number, and it's n, and it designates the size. So it designates the size of the orbital. Larger values of n corresponds to larger orbitals, as we see here, where we have 1s, 2s, 3s, and 4s. We can see an increase in the size of the orbitals. The allowed values for n are integers, so 1, 2, 3, and so forth. So a collection of orbitals with the same value of n is frequently called a shell, right? So when n is 1, that's the K shell. When when n is 1, that's the K shell. When n is 2, that's the L, etc., etc., right? So each shell, and from high school, you probably would have heard about shells. So basically, a collection of orbitals with the same value of n is frequently called a shell. Remember that. L, which is our angular momentum quantum number, it signifies the subshell, right? And this describes the shape of the orbital. And L values range from 0 to n minus 1. And so, if n is equal to 2, then L can be 0 or 1. And so here we have various values of n. And as we said before, L values range from 0 to n minus 1. So when n is 1, then the only option is 0, right? When n is 2, then L can be 0 or 1. When n is 3, then L can be 0, 1, or 3. And then when n is 4, then L can be 0, 1, 3. 0, 1, 2, 3, right? So what we want to say here is that each number here corresponds to a particular shape, orbital shape, right? So when L is 0, that is the s orbital, and that is the spherical shape that we have seen here. This is a spherical shape, so this is the s orbital, and that occurs when our angular momentum quantum number L is 0. As opposed to P, let's go back to this P orbital here that we saw here. This is an example of a p orbital. Is shaped like a dumbbell or a 8, and that occurs when L is equal to 1, right? So in a little we'll see the shapes of the others, but those are the two major ones that we're looking at here. And we'll also see in a little bit the energy states. So generally you have one s orbital at each n at each energy level, and you have 3p, right? And you have 5d, right? We're not really going above d, right? So just focus on 1. N is equal to 1, 2, 3. Everything below here, we're not really going above 3. All right, so for the magnetic quantum number ML, this describes the orientation of the orbital in space. So ML are integers that depend on L. So L, and this is our energy states that we just mentioned a while ago. So L is so for ML, when L is equal to minus L, 0 to positive L. So ML identifies the number of energy states for each subshell. So we just mentioned the subshells a while ago. This is ML territory. For an S subshell, a single energy state, right? For PDF subshells, we have 3, 5, and 7 energy states, as we saw here on this side. So 1, 3, 5, and 7. All right, so let's pick one of these rows to go into. So let's pick n equal to 3, right? So if n is equal to 3, then what is L? What did we say L was? L is from 0 to n minus 1. So from 0 to 2, right? So that's why we have 0, 1, and 2 as can be L. So this is the same thing here. We have 0, 1, and 2 that we have here, 0, 1, and 2. So if this is L, then what is ML? What is the orientation? And as we said, ML are integers that depend on L. So let's look at the different L. So for 0, there's only 0, right? For 1, when L is equal to 1, then you can have -1, 0, or +1. When L is equal to 2, and remember what we said, ML is equal to -L, 2 plus L, right? So when L is equal to 2, then you can have -2, -1, 0, 1, and 2. So this correlates to our D, right? Or D orbital, right? So 2 would be equal to D, and we have 5 energy states. P is equal to 1, and we have 3 p orbitals, right? 3 energy states, and S is equal to 0 s orbital, and so we generally just have 1 s orbital at each level at each principal quantum number. All right, so the number of available electron states for initial shells and subshells, right? So I have put here prior knowledge, right? So what previously you would have known your electronic configuration to, for example, be 288. That is similar to what we're talking about here, right? Just that we have broken down these further into these electrons would be broken down in further into subshells, right? And so what you would have known, those 288 would represent the shells, right? But you're taking it a step further now to look at these subshells. Where are these electrons located? And so, as usual, let's pick the same one that we picked here, which was n equal 3, right? So when the principal quantum number is equal to 3, that is equal to our M shell, right? And from there, we have, if n is equal to 3, then we have 0, 1, 2, as we just worked it out. And as we said, 0 is S, 1 is P, and D is 2, right? And so we have 1 s orbital at this energy level. We have 3, and that's 3 here, 3 p orbitals at this energy level, so that's -1, 0, and +1. For the d orbital, we have 5 energy levels, so -2, -1, 0, +1, and +2, right? And so the number of electrons per subshell, right, would be equal to 10, right? So there would be 2, 4, 6, 8, 10. So 2 electrons would be in each energy state, right? So 2, 4, 6. So 6 electrons in our p orbital, and we'd have 2 electrons in our s orbital. So that's how we work it out, right? So as I said, we're in going from your high school knowledge of electronic structure, these are the shells, these shells that you would have been familiar with. We're taking it a step further to look at the subshells, right? So that is S, whether it's in an s orbital. So for quantum number 1, we only have S, 1 s orbital. For quantum number 2, we have S and P, right? So we have 1s and 3p at the principal quantum number 2, and we just worked through 3 a while ago. So An S subshell has one orbital, as we saw, which is spherically shaped. So it's shaped like a ball. So if we were to measure the electron, where the electron was within a S subshell many times and plot the results on a graph, you would get something looking like this, right? So as I said, it's a probability distribution. So it's a probability of finding the electron at X position. And here we see that, yes, it could be out here, but that probability is very low. A lot of the times when it is measured, it's measured close to the nucleus, and that is why the proposed structure of the S subshell is spherically shaped. For the P subshell, as I said, it looks like a dumbbell shape with electrons on either side of the nucleus in teardrop shaped loops. So this is the image that we have seen before, but just didn't mention that one would be aligned along the Z axis, one along the X, and one along the Y. So we have three orientations, and as we said, when L is equal to 1, as required for a p orbital, we have three energy states, and that is pz, px, and py. As we said, 2 electrons would be assigned per energy state. And for our d orbitals, as we see that it's getting more and more complicated, we have 2 lobes generally. This one looks a little bit, well, more than a little bit different from the others, right? So essentially we have 5 orientations of the d orbitals, and therefore L is equal to 2. And so we have 5 energy states, and we can have 2 electrons in each energy state. So initially we mentioned 4 quantum numbers, but we didn't mention the 4th one, which was the electron spin quantum number ms, and that is used to specify an electron spin. So there are 2 possible directions of spin. So it's either spin up or spin down, right? So it's either up or down, and the values are +½ or -½ So just to summarize our quantum numbers, we mentioned the principal quantum number n, and that determines the size. Remember the angular momentum, and it determines the shape. Remember the magnetic ml, and that is the orientation or the energy states, and that is required to describe an atomic orbital. So 2, if we see here, 2 represents here the principal quantum number, p represents the angular momentum, and that is, the shape of the orbital, and x here is related to the magnetic quantum number, and of course that is related to the energy states. And for ms, direction of spin are required to describe an electron in an atomic orbital. So we have to look at a few more scientists which helped us to define, how do we put our electronic structure together. And one such scientist is Pauli. And he proposed the Pauli exclusion principle, which says no 2 electrons in an atom can have the same 4 quantum numbers, the same values for n, l, ml, and ms. He also said that although the first 3 quantum numbers identify a specific orbital and may have the same values, the 4th is significant and must have opposite spin, right? So if an electron or orbital, well, the first 3 identifies a specific orbital, and the 4th one, it is significant and must have opposite spins. And finally, a set of quantum numbers is specific to a certain electron. That's what Pauli said. So that leads us now to our question, which says an electron with n equal to L equal 1 ml is equal to -1 and ms is equal to +1/2 is found in the same atom as a second electron with n equal to L equal 1 and ml is equal to -1. What is the spin quantum number for the second electron? So if you guessed -1/2, you would have been correct. Because since the first three quantum numbers are identical for these two electrons, we know that they are in the same orbital, right? And as a result, the spin quantum number for the second electron cannot be the same as the spin quantum number for the first electron. And so this means that the spin quantum number for the second electron must be what you had, which was -1/2. All right, so I do know that this side is a little bit wordy, but let's read through it slowly. So we must mention our effective nuclear charge, which is Z effective, right? So the positive charge of the nucleus experienced by the electron in the 2p orbital is actually diluted by the presence of the 2s electron density close to the nucleus, right? And so the 2s electron screens or shields the 2p electron. And I have a little demo here. If we have our positive center here, and we have the 2s electron and we have the 2p electron, this electron will shield, the 2s1 will shield the 2p electron, and so the 2p will feel less of a pull from our positive center. And so the nuclear charge experienced by the electron in the 2p orbital is actually less than that experienced by the electron in the 2s orbital. And so take into account these effects, it becomes necessary in many electron atoms to replace the nuclear charge Z by the effective nuclear charge Z effective. The value of Z effective for a given atom actually varies for different orbitals and depends on how the electrons there are in R and in which orbitals they reside. And so the 2s orbitals are more penetrating and they shield the 2p orbitals, as we said. And so the electrons in the 2p orbitals experience a lower attraction, as we also said, and are therefore higher in energy. And if we are higher in energy, that means they're less stabilized than the electrons in the 2s orbitals. And we can have similar arguments for our principal quantum number 3 orbitals. And that is why here, as we said, the 2p orbital would be higher in energy and therefore less stable than our 2s electron, and that is the reason why. And we said that there's a similar arrangement here for our 3s, 3p, 3d, and our 1s is even lower in energy and more stable. And here we have a schematic representation, it's not drawn to scale, and a representation of the energy solutions for n equal 1 to 3 of the Schrödinger equation for a many electron atom, right? So it's not drawn to scale. However, it's showing that there are different energy levels for the different shells. All right, so coming down to the end now, we have our electronic configuration. So having said all of that to get to this, right? And so we saw iron before, and we saw that the it has 26 electrons. But how do we write the electronic configuration? Well, we write it as 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. And here, notice that we said here that the energy level was not drawn to scale, because what we're seeing here is that the 4s energy level is actually lower than the 3d energy level, right? So that means that that is a more stable arrangement. So we spoke about Huns, right? And Bohr says that the electrons are added to the lowest energy orbitals first before moving to higher energy levels. So as we see here, the 1s is full, the 2s is full, the 2p is full, the 3s is full, the 3p is full, the 4s is full. So all of them, the lowest energy levels have to be filled before higher energy orbitals, right? So 4s is generally filled first before the 3d orbitals. So notice what we said about the shell, right? In high school, you would have learned about the electrons in a particular shell. But at this level, we're saying that the shell is equal to a particular principal quantum number. So our N shell, our K shell would be our 1s orbital only, or our L shell would be our 2s and our 2p, the electrons in our 2s and 2p orbital. Or M shell would be our 3s and our 3p orbital. So that would be similar to what you would have seen in high school, where you'd have seen 2, 8, 8, right? But we're going deeper into those subshells. And I have it here. So instead of the electronic configuration for potassium being 2881, we write 1s2, 2s2, 2p6, 3s2, 2p6, 4s1. So 2 electrons in the 1s orbital, so that's 1s2. 8 electrons in the 2s and 2p orbitals, so we write 2s2 and 2p6. 8 electrons in the 3s and 3p orbitals, so we write 3s2 and 3p6. And then we have 1 electron in the 4s orbital, and so we write 4s1, right? So just to compare, or for you to relate prior knowledge to what we're talking about now. So you would have learned about the shells. Now we're learning about the subshells, right? And point to note is that we fill the 4s orbital generally. There are 2 exceptions, and we'll talk about the 2 exceptions in a bit, right? But generally, we fill the 4s orbital before the 3d. All right, so there's another person. So we talked about Pauli, Bohr, and now we're going to talk about Huns. So Hund's rule said that the most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. And so here we have an example of carbon. So it has a total of 6 electrons. So of course, according to the Bohr principle, we fill the lower and then we build up to the higher energy level, right? And we put 1 electron in each before pairing, which is what Hunt said. And the 2p orbitals are of equal energy, and another way of saying equal energy is degenerate, right? And so here Hunt is saying that this is the most stable arrangement when you have 1 electron in one 2p orbital and the other one in another 2p orbital, and you would have the same spin. So the most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. So notice, all right, so here we have spin up and spin down. Spin up, spin down. And we have spin up, spin up. And if we were to add a third one, it would go here. And then now, because it has to be filled before we go another, well, let's go to iron or potassium here, right? So here, notice that all of the lower energy levels has to be filled before we go to a higher energy level. Yeah, this is a better example for iron, because notice that we have spin up, spin up, spin up. So all of this would definitely support what Hunt is saying, that let's go back to that slide that says the most stable arrangement of electrons is one in which the number of electrons with the same spin is maximized. So here 1, 2, 3, 4, 5 electrons have the same spin, right? And so once you add other electrons, then you will add the other spin, right? Spin down, spin down, spin down, spin down, right? But this is the most stable arrangement when you have the electrons in the same spin being maximized. So another important point in writing our electronic configuration is that the electron configurations of the first 10 elements illustrate the order of subshell filling, right? So here we have hydrogen with just one electron, helium with 2 electrons, but we have to fill the 1s orbital before we go to the 2s orbital, right? For lithium, right, we add an extra electron here in the 2s orbital. For beryllium, we add another one in the 2s because obviously it has to be filled before we go to a higher energy orbital, right? For boron here, we add an electron in the 2p orbital. And remember what Hund's rule said. So for carbon, we have to add another electron in a different 2p orbital with the same spin. And for nitrogen, we're seeing here in a third 2p orbital with the same spin. So we're seeing that, let's go back to the rule. The most stable arrangement of an electron is one in which the number of electrons with the same spin is maximized. So clearly for nitrogen here, we're seeing that the same spin is maximized. And of course, we continue to add or electrons, oxygen, fluorine, neon, right? And here, I just wanted to highlight 2 exceptions to the 4s rule. So generally, we have been saying that we add the electrons, we fill the 4s orbital before we go to the 3d orbitals, but there are 2 exceptions to this rule. And this is chromium and copper, right? Notice that when the 3d orbital is half filled, that is 5, and full for copper, which is 3d10. So 3d5 and 3d10, we have 4s, right? So the electron is in the 4s. One electron is in the 4s orbital. When we have the chromium, the orbital is being half filled, and when the 3d orbital is full, then the 4s orbital has only 1 electron, right? So these are the 2 exceptions to the rule which I just mentioned. And so the rules for electronic configuration says electrons will reside in the lowest possible energy orbitals, and that's what Bohr said. Each orbital can accommodate a maximum of 2 electrons. As we have seen, each orbital has 2 electrons. Electrons will not pair in degenerate orbitals if any empty orbital is available. So that's what Hunt said, which is seen here. So if we have, meaning degenerate means same energy. So all 3 2p orbitals here are of the same energy. And so the electrons will not pair in such an instant. It will only pair when this situation is filled, and then we have we're adding other electrons, right? And so electrons will not pair in degenerate orbitals if an empty orbital is available. And finally, orbitals will fill in this order. So 1s to 2s to 2p to 3s to 3p to 4s to 3d, right? So that is how it is filled generally. Remember the 2 exceptions with copper and chromium for the 4s orbital. All right, so we have a question here which says, write the electron configuration or electronic configuration and give the orbital diagram of a calcium atom, and the atomic number is 20. So it has 20 electrons therefore, right? So each s subshell can contain a maximum of 2 electrons, whereas each p subshell can contain a maximum of 6 electrons, right? So this is a solution. So 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So remember that the 4s orbitals fills before the 3d orbitals, and there are 2 exceptions, as we said, with copper and chromium. So this brings us to the end of this, our first lecture, and all I have to say is that's all for now.